Charley Lineweaver started out studying history and English. Then he went looking for the oldest light in the universe. In the early 90s, he was part of the NASA team that found the first fluctuations in the cosmic microwave background, the faint afterglow of the Big Bang. Stephen Hawking once called it the biggest scientific discovery of the century, maybe of all time. That work later won his supervisor a Nobel Prize. Since then, Charley's turned to a bigger question: are we alone? His answer is unsettling. He co-developed something called the Gaian Bottleneck, the idea that life doesn't usually fail to start. It starts and then it dies because it can't learn to regulate its own planet fast enough to survive. Which means the interesting question isn't why haven't we found aliens, it's how we ended up being one of the lucky ones. I'm Aidan Mill, and this is Uncomfortably Curious. Charley, you started studying history and English, and then you ended up working on the Cosmic Background Explorer mission. So that sort of helped map some of the earliest light in the universe. What actually happened there? What was that transition like?
Oh, well, what happened was I went to the State University of New York at Binghamton, and I was always good in science. I always loved science. But the State University of New York at Binghamton, the best professors there were in English and history. And I was told by a wise aunt and others that you should always take, at the university, always take the best professors. So that's what I did, and I don't regret it. They were incredibly good historians and English professors. So, I think everybody should study English just to become fluent in what they think is their own native language, which often is not. So anyway, I studied English and history, and then I traveled around West Africa, and I saw people who were dying because they were not literate. They didn't know how to read. And so I thought, hey, I better get literate in my own language. So I went to Brown University to become fluent in English. And then I was so enamored of French, traveling through French West Africa, that I spent a year in France learning French. So, but my love for physics and science never went away. And my dad was a high school biology teacher, so I started studying physics, and then I went to Japan and studied physics. I studied physics in Germany. Then I entered the PhD program at Berkeley in California, and that's when I joined the team that discovered the fluctuations in the microwave background radiation, the oldest light you can see with a telescope. And the work we did there got George Smoot, my PhD supervisor, a Nobel Prize. I think it was in 2006 for physics.
Wow. So, for people who don't know, I guess what did that discovery of the cosmic microwave background actually tell us, and why did it sort of matter so much?
Well, it made the headlines all over the world, and Stephen Hawking called it the greatest discovery of the century, if not of all time. And the reason he said that is because when you look up at the stars, you see all the stars you see in the night sky are in our own galaxy. And then when you look further away, you can see other galaxies. And then you can look at the most distant galaxies. You may have heard of the James Webb Space Telescope. They're looking at galaxies that are very, very early. But the microwave background radiation is the oldest light you can see. Essentially, you're looking at the Big Bang. It's as far back as you can see in the universe with light. It's kind of like, when you look at the sun, you don't look into the sun, you see the surface of the sun. It's called the photosphere. Well, the cosmic microwave background is like the photosphere of the universe. You're looking back in time, the universe is getting hotter and hotter. Eventually, it gets so hot that hydrogen cannot exist. You have a proton and electron in hydrogen, and if it's so hot, then they separate, they ionize, and so you have free electrons and free protons, and that's what makes the sun opaque, why you cannot see into it. It's also what makes the universe opaque, and you cannot see further back into the past because of this separation of the electrons and the protons, because it is so hot. And that's the surface of last scattering. That's the surface that we're able to see. That surface we know dates from about 500,000 years after the Big Bang, about 390,000 years after the Big Bang. So it's the earliest thing anybody can see with light. And so what we saw in this radiation were hot and cold spots, which are interpreted as the seeds of large-scale structure. They are overdensities and underdensities, hot and cold spots, which later turn into giant voids and giant aggregations of galaxies. So it is those hot and cold spots in the cosmic microwave background are the seeds of all the structure we see in the universe around us and nearby.
Yeah, I mean, it's a bit mind-boggling to be honest, especially if someone who doesn't study it. But do you remember the actual like what the feeling was yourself and the team when that actually that discovery sort of happened?
Well, a lot of people have asked me that question, and it's interesting. Everybody's looking for the eureka moment, and like in most science, there aren't eureka moments because you say there is a eureka moment, but it lasts for about a year and a half. In other words, you think, oh, a little bit more confident, a little bit more evidence. Check this, check that. Oh, that's good. Check this, check this, check a little bit more. Check this, check that, et cetera, et cetera. And George Smoot describes this in his book about our discovery. And he focuses on one particular point where I make a plot, and I slide it under his door and says "Eureka" with a question mark. And so, yeah, it was a wonderful thing to discover, and we knew we were onto something important, but it was much more grueling and long put out and a lot of work.
Yeah, I guess. Okay. Yeah. In hindsight, obviously, you can see the totality of the discovery a bit clearer, can't you?
Yeah, we didn't jump out of a bathtub and yell through the streets like Archimedes did.
That's a shame.
Yes, it's a shame.
Now, moving on to sort of one of your other ideas that I had heard about before. I'd sort of read about your work, but didn't know a lot about until I researched it a bit more. But the sort of Gaian Bottleneck problem, or I guess however you want to describe it. So most people would assume that it's actually a really hard issue to get life started on a planet or our planet or any planet, but you've got a bit of a different argument on that side. Can you explain what the Gaian Bottleneck is and says?
Yeah, so when we look around the universe, so far we haven't detected any advanced civilization. We haven't found any aliens. And so this is called the Fermi paradox. Where is everybody? Now, where is everybody assumes that there are lots of Earth-like planets. On these Earth-like planets, life will evolve. With this, life will evolve intelligence and then create technology, and then they will colonize the galaxy. But if that were the case, if those three assumptions were correct, then the galaxy would already have been colonized hundreds of millions of years ago. But we don't see that. So where is everybody? So which of those assumptions is correct? Now, it could be. Now, we know from recent analyses that Earth-like planets are common. About probably if you look up at the sky, probably about 1/10 of the stars you see have something resembling an Earth-like planet going around it. So that's a lot of Earth-like planets. Now, Earth-like means essentially wet and rocky planet. And in close to the habitable zone, that's where its distance from the host star is compatible with having liquid water on the surface. All right, so that's what an Earth-like planet is. Now, so where is this life? Why don't we see it? Well, one reason might be what's called an emergence bottleneck. In other words, the recipe for the origin of life is so complicated that it's a rare thing that doesn't happen very often. That's called the emergence bottleneck. Another bottleneck might be the intelligence bottleneck, and that is, there's life everywhere, but it doesn't evolve into things that can make technology, human-like technology. Remember, on Earth, human-like technology is a species-specific characteristic. We are the only species who makes rocket ships and makes radio telescopes and electronic engineers. And so it's a species-specific trait of Earth. And to pretend that it's something generic is a very, I think, an inappropriate extrapolation. It's kind of like saying, oh, we're so good, everybody should want to be like us. And that's what I call the Planet of the Apes fallacy. Anyway, there's an emergence bottleneck. Maybe there's a technology bottleneck. Maybe there's a self-destruction bottleneck, and that as soon as some civilization becomes technological, it develops weapons that can kill itself, and then eventually it has World War X, and then it kills itself. Once you have the ability to very, very powerful weapons, that's what you can do, and that's what may happen to every civilization. Remember, this is something that has to happen to every civilization, because if it doesn't happen to one, that one will colonize the entire galaxy, and so then we wouldn't have the Fermi paradox. So the idea behind the Gaia bottleneck is the following. We know that wherever you are in the universe, when you have a star, you have some type of planetary system. In the first billion, but particularly the first half a billion years, those planets have to build up. They build up by having collisions. boom, boom, gets bigger, boom, boom, gets bigger. And that's how the Earth formed. That's how the Mars formed. That's how Venus formed. And that's how probably every Earth-like planet in the universe forms, by accretion, by bombardment, accumulating material and getting bigger and bigger. And then it runs out of material, and then it rests at that size, final size. So that's called the early heavy bombardment. And that's, like I said, probably a feature of planetary evolution everywhere in the universe. Now, these bombardments are so big that if there's anything interesting happening on the surface, it would get completely wiped out by any impact of an object larger than about 200 kilometers in diameter. Remember, the object that wiped out the dinosaurs, or most of the dinosaurs, the non-avian dinosaurs, that happened about 65 million years ago, and that probably had only a diameter of maybe 6 kilometers. So if you want to wipe out all life on a planet, you need something that's 20 to 30 times bigger. So about 200 kilometers. And 200 kilometer objects are very, very common in the first half a billion years. They're very rare now, but in the first half a billion years, they're very, very common, because that's the gigantic objects that are part of the debris, the protoplanetary disk that is forming around every star as part of its accretion and part of its planetary formation. So, are you with me so far? That makes sense?
I am. Yep.
Okay. So the first half a billion years, boom, 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 and then it slowly goes down. Boom, less frequent, and then it calms down to something that we've had for the past 2 or 3 billion years now. So now, interestingly, when we study the origin of life on Earth, we know that life started about 4 billion years ago. Now, 4 billion years, just the sun and the Earth are about 4.5 billion. So life started somewhere 4 billion, maybe 4.2, maybe 3.9, maybe 4.3, in that region. So it formed possibly sometime at the tail end of this, what I've described as the early heavy bombardment. So, the largest object that hit was 200, and then it went down to 100. Maybe the largest object was 50 kilometers in diameter. And that wasn't quite big enough to extinguish all life on the planet. And then ever since then, we've had life on Earth. Something like that. Now, but bombardment isn't the only... Well, bombardment is interesting because it can create what are called runaway conditions. You can distinguish between feedback mechanisms, positive feedback and negative feedback. You probably have a thermostat in your room, and you set it at a certain temperature, and then it's too hot, you make it cold. Too cold, you make it hot. That's called negative feedback. There's also called positive feedback. It gets a little hot, that makes it get a little hotter. That makes it get a little hotter, and then poof, you have runaway. And that's what we think happened on Venus, for example, with the CO2 atmosphere. It probably was more habitable earlier on when the sun was less luminous. And then we got CO2 built up. It had a greenhouse effect, and then a runaway greenhouse. Now it just gets hotter and hotter and hotter and hotter, and then it's just too hot for life to do anything. Remember, the surface of Venus is hotter than your oven, the highest temperature of your oven. And then you also have runaway cold. You can have what Mars did. It runs away, the atmosphere goes away, and then it gets colder and colder because it's further away from the sun. Atmospheres essentially act as like a blanket to a planet. And Venus has too thick a blanket, and Mars has too thin a blanket, and our blanket seems to be about right. Now, getting about right is something that probably has a lot to do with the existence of life. Like right now, your body is about 37 degrees. My body is also 37 degrees. How does that happen? Well, we have regulators. So there's a homeostasis that your body actively does things to maintain that temperature. Even if it's outside, it's 10 degrees outside, your body's still 37. It gets to be 40. I was recently in Egypt. It was 42 degrees. My body was still 37. It was trying to cool itself with sweat, etc. Excuse me. So the point is that life seems to have this homeostasis about it. And at least we just talked about individuals. But what about ecosystems? What about the global level? And the idea that life would modify the entire environment of a planet to keep it habitable is something called the Gaia hypothesis. And it's questionable, it's controversial in some circles, but I seem to have swallowed the Kool-Aid on this, and I think that it makes a lot of sense that an ecosystem could do that. There's a lot of literature on this, and I read a lot of it, and so I'm convinced that there's something to this. Now, if there is something to this, you can ask the question, when did life start to be able to regulate the biochemical cycles, the chemical cycles, initially abiotic ones, that regulates things like the albedo? You know what the albedo is? Albedo is how much you
No.
get reflecting. You know, if
Okay.
it's sunny outside, you can make a choice between wearing something white or wearing something black. Black absorbs the sunshine, white reflects it. If you want to stay cool, white is the better choice. Now, the planet, if you look at the Earth, you can see that clouds reflect light, and so they keep it a little bit cool, at least some types of clouds. But let's work with ice. You know, you have the two ice caps on Earth, and when sun hits those ice caps, it reflects a lot of the light, and so it doesn't heat up. But if snow were black, then it would melt, warm it up, and warm up the whole planet. So that would be changing the amount of ice on Earth changes the Earth's albedo. And so if you can control the reflectivity of the Earth, then you can control the Earth's albedo. And that controls the Earth's temperature, just like wearing white or black controls your temperature. So that's one mechanism by which life, by changing the colors and changing the amount of snow, for example, can regulate the temperature of the Earth. Another is you may know that you're breathing oxygen right now, right? The Earth, the atmosphere you're breathing is about 20% oxygen. All of that oxygen is produced by the plants outside. So that happened about 2.4 billion years ago at the Great Oxidation Event. So the oxygen in the atmosphere is controlled, regulated by life. Now the CO2 is also controlled by life because those plants are breathing in the CO2 and putting out oxygen. So the atmosphere of a planet is integrally, it's integrated into the biosphere. The biosphere controls it, regulates. For example, very early on, we know that the sun used to be fainter, and yet the temperature, the surface was not frozen. And that's called the faint early sun paradox. One solution of that is that life was making methane. Methane is a stronger stronger greenhouse gas than CO2. So if you have plants producing methane, well, it's like a really, really thick blanket that's keeping it warm, and that was necessary because the sun was so faint. And so, but you also have things called methanotrophs, which breathe in the methane. So if you have a source and a sink that are both biological of a gas that strongly affects the temperature of the Earth, then you have a way to regulate the temperature of the Earth. Now the question is, how early can such regulation happen? During this bombardment, the early bombardment, you have boom, 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 and you can easily get runaway cold or runaway hot. But if you have some type of regulation, a thermostat regulated by life, then you can keep it from going too hot and keep it from going too cold, and that would be homeostasis, that would be Gaian regulation. Excuse me. And but the question is, how soon could life learn how to do that? I mean, life pops into existence, it can't already know how to do that. It has to evolve. And the question is, how rapidly can such a thing evolve? And what the Gaian bottleneck, now we get to the Gaian bottleneck part, the Gaian bottleneck is the idea that such abilities very, very early on, which it's necessarily very, very early on, because otherwise it would go runaway hot, runaway cold. But such abilities very, very early on are rather rare, might be rather rare, and then if that's the case, then you have a Gaian bottleneck. So life, there's no bottleneck associated with the emergence of life. There's no bottleneck associated with producing Earth-like planets, but there's a bottleneck associated with life figuring out how to regulate the atmosphere early enough so that it doesn't go runaway hot or runaway cold.
Okay, right. Yeah, sounds very, very complicated.
But
So-
notice that this is also a potential explanation for the Fermi paradox, and that is there's no emergence bottleneck. The chemistry is not difficult. There's planets are everywhere, and maybe intelligence just evolves from life. But if we have a bottleneck associated with the quick ability to regulate the atmosphere of a planet early on, then that could explain why there are so few life forms that we know of in the universe today.
Yep. Yeah. Okay. Right. So then, yeah, like extinction, or the failure to, progress is the rule and not the exception, sort of thing.
That's the hypothesis. We're saying that
Yeah.
that might be part of the explanation for why we don't see any life forms elsewhere. Of course, I think another very plausible explanation for in answer to the Fermi paradox is that human-like intelligence is not a convergent feature of evolution. Life forms everywhere in the universe are not trying to become human.
Yeah, I was going to ask you about that as well. So and you've got a few lines of evidence about how on Earth, in sort of rather excluded areas for long periods of time, we didn't see that sort of rapid progression of intelligence occur naturally.
Well, yeah, that's right. I would never call it intelligence. I would call it human-like intelligence because I think every life form has the type of intelligence that has kept its ancestors alive. Dogs can smell much better than we can, so obviously it was much more important for their ancestors to have that sense of smell. Our sense of smell is terrible, and I envy every dog when I go for a walk. But so every creature on Earth has some type of intelligence has the type of intelligence that has been useful for the survival of its ancestors. So you can ask the question, what is human-like intelligence something so generic that it should evolve elsewhere? And I think the best way to answer that question is with data. And that data, the experiments to test this hypothesis have already been run. They have been run over the past 200 million years. The names of these experiments are New Zealand, Madagascar, Australia, South America. These are all for long periods of times, these continents with thousands and thousands, maybe even millions of species, had the ability to evolve things with big brains that could do technological things, but they didn't. And so their brains did not get bigger. And so there's evidence from what's called paleoneurology that we should not expect things to normally have bigger brains and then become technological. And a lot of people say, wait a minute, that's such an important thing that of course it should. But the evidence points exactly in the opposite direction, and that it doesn't. When Europeans first landed when humans first came to Australia about 50 or 60,000 years ago, there were not kangaroos who had fire or firearms. And so many examples millions of examples of species that did not evolve towards technology are, I think, very good evidence that human technology is not a convergent feature of evolution that we should expect elsewhere. In fact, it is a species-specific characteristic, and anything that's species-specific is not something you should expect to have evolved either elsewhere on Earth or elsewhere in the universe. It's a little like English. English is a very specific language. It's so specific and quirky that you should not expect it to have evolved on Krypton or any other exoplanet that has some type of life there. So I think that, matter of fact, not only human-like intelligence, I think maybe even what we call life is such a quirky thing that we should not expect it elsewhere. But that's another issue.
Yeah, it does. I haven't actually heard before you've spoken about it, that side of the argument about the experience already been run several times on Earth, and we didn't see the evolution take place in that way. But then I guess, well, speculation all you like, go nuts. But in terms of our evolution, then specifically, humans and sort of other human-like, ancestors, then our brains tripled over this, course of a few million years. What do you think actually went on then? Obviously, there's a certain set of circumstances.
Well, this is highly controversial. People talk about it all the time. My favorite model is the fire. So the 2 to 3 million years during which our brain went from about this big to about this big, tripled in size, seems to correlate with the time frame in which we started to learn how to use fire. I think that would be Homo erectus about 2.5 million years ago, and since then. And so at least there's a guy, Richard Wrangham, is a Harvard guy who wrote a book on this. I can recommend that. And And it also, the diminution of your jaw. You don't need to have such big jaw muscles to chew up food that if it's been cooked. The length of your small and large intestines have gotten shorter because you don't need as much processing when you have already processed it with cooking it. So I think that had a lot to do with it. But then you have to ask the question, well, how often do creatures learn how to use fire? And then, well, what do you mean by use? I think some people have maintained that sometimes birds, pick up a burning stick and then throw it somewhere to burn more stuff so they can, I don't know, find more food. Whether you want to call that the use of fire or not, I'm not sure. But it's a kind of use of fire, but it's certainly not like cooking, or it's I don't know. I wouldn't call it intensive cooking that's regular. You'd rely on lightning bolts to start the fires that you can't start fire yourself.
Yeah, I think that it's a very interesting question, but I don't know. Hopefully, someone can figure out a way to test that and figure out why that might have happened. But it seems like there's too many variables.
Let's just say there's a lot of correlation between when we started to use fire and the size of our brain, and also the amount of calories. More calories are available in food when you cook it. So I think, and if your brain is very energy intensive, it needs a lot of energy. Therefore, it would need the higher input of the calories from cooked food. And so those are correlations. It's not necessarily cause, but I suspect that it is cause.
Yeah, okay. So when we're, obviously, and naturally, we always have this human lens of when we're talking about, like you said, the human-like intelligence and looking for that sort of life elsewhere in the universe. But does it all come back to that bias and sort of the vanity in ourselves for searching for life out there, or is it literally just another excuse because we're looking for ourselves out there in one form or another?
I don't think there's anything wrong for looking for yourself. What's wrong is having inappropriate speculation. Actually, having inappropriate expectations is very important for discovery. Just ask Christopher Columbus. He was terrible at estimating the size of the Earth, and because he thought that the Earth was much smaller, he thought, hey, I can go all the way across this, whatever it is, this ocean that separates Europe from Japan and India. I can go across. And it was just I think he thought that the Earth was like 1/3 the size it actually is. So a really stupid mistake. But what was important was he went and looked. He went and searched. And so searching is always important, even if it is motivated by terrible ideas. So I think SETI falls directly into this Columbian category of searching with terrible motivation. I think that there's absolutely no evidence we have that suggests that human-like intelligence, the developing of technology, is something that we should expect elsewhere. And yet, I think, and that's the motivation for most of SETI. And yet they are out there searching, and I think that's really important. So I support SETI, even though I think they're poorly motivated or inappropriately motivated.
Yeah, right.
I think they should be motivated by searching. Searching, almost neutral searching is, even not. I mean, Columbus was not neutral. He knew exactly what he wanted to find, but he was just so wrong, and he found something interesting. I think SETI may very well do the same thing. SETI is the search for extraterrestrial intelligence.
Yep, yeah, that's right. I think both aspects can be true at the same time there. I've thought when I hear that we've sort of sent radio signals out, decades ago, and trying to sort of wait for a signal back, I always think it is a bit strange to sort of have the assumption that we will hear radio signals back because whoever's out there will have that as a type of technology. Is that a fair, I guess, question about it, or?
Well, what's important in the Fermi paradox is how far away these supposed human-like electrical engineers are. And if they're within 10 years, 20 years, 100 years, 1,000 years, then, we can wait that long. But if they're far enough away, then the delay from we send it out, it takes, let's say, 10,000 years to get there and 10,000 years to get back. That's a long time, and a lot of things happen in 10,000 years. So it's kind of like, you probably, have you ever talked with geostationary satellite communication? The geostationary satellites are about 30,000 to 36, they're 36,000 kilometers away. And light travels at about 300,000 kilometers. So that's like a tenth of a second. So you have a tenth of a second out, tenth of a second back. That's 2/10 of a second. add another tenth of a second for latency, and you get a third of a second latency in your communication, and that screws up a lot of things. You really, what do you say? Then you repeat, and you talk over each other. You can imagine if the latency, instead of a third of a second, you have 10,000 years, and so it's a really embarrassingly ineffective way to communicate. But I say again, the evidence we have is that we should not expect human-like intelligence, human-like technology elsewhere, and so I don't think you need to worry about this. I think the universe is stranger than we can imagine, and projecting human technology out there is not a very strange thing, and it's not. The evidence we have suggests that it's not there. It's kind of like I said, it's like imagining that we can speak English and just, hello out there, how are you? And then you're speaking long English sentences, expecting the other people whatever they are, to speak English. And it's just, no one in the right mind thinks English is a universal language. They think math is. Now that's an interesting idea. I think math is not a universal language, because when you try to communicate with a dog or a dolphin or, I don't know, a cockatoo, you don't use, sometimes you could use music, and you can use touching, feeling. But using math to dogs, 2 times 2 dog, doesn't work. Talk to a dolphin 2 times. They'd rather be touched, or they'd rather hear music. But those are the more based on interspecies communication on Earth. Those are more likely to be that methods to communicate with other species rather than mathematics. Now I know that also is something that's a minority view. You might recognize that I'm giving you a bunch of minority views. Most scientists believe that more conventional views, but these are uncomfortably non-vain, unconventional views. So that's what you like your viewers to have. You said uncomfortably curious. So I think a lot of things we're finding out about ourselves are uncomfortable, and therefore people don't want to hear them. And
definitely.
I think you're bucking a trend here, because people want to hear what they want to hear. And so maybe you have like 0 viewers of your podcast or something, and you could blame yourself for that by putting uncomfortable. You put comfortable curiosity in there, you get more people listening.
Maybe might appeal to the masses a bit more, but that would be going against what I'm trying to build. To be honest, so, yeah, maybe a few hundred years ago, I might not be doing this. I might have been locked up somewhere.
But, shaved your head completely, put a big sign, and shunned you.
Exactly. That's an interesting point about the mathematics, because I don't think, any time I hear any scientist speak about anything about the universe, they always mention that mathematics is a universal language.
Again and again and again. And I just
ad nauseum.
The best way to test that is to try to communicate with other species on Earth, and it doesn't work. It doesn't work at all, and some things do work. Talk to any trainer of a horse or trainer of a dog, and they know what kind of works. And that is an emotional attachment, and sometimes music. Guys go with violins out in rafts, and the dolphins come around and say, "Oh, that's interesting. What is that?" Because their whole life is done with sound. You can think of, they see with sound.
Yeah, and that also makes me think about the possibility that various other life forms would have types of senses that we can't even comprehend and have no idea how that would actually interact.
You don't need to imagine that. Just try to talk into a plant. How do plants communicate? They do communicate, but they communicate in ways that not with sound like we are, but with some type of chemistry that gets put into the atmosphere, and then they get chemical receptors. So, excuse me. So plants do communicate with each other, but we're just right now finding out the very basics of how that happens. Fungi probably do too, and again, we know almost nothing about it. So before we speculate so wildly about life elsewhere, we have to figure out how the various wonderful, interesting ways that the life forms around us communicate with each other, and get out of our sonar monopoly, sonar focus.
You mentioned earlier about the habitable zone for planets. So is the definition literally just a region that potentially could have liquid water on it, or is there more sort of complications
to have liquid water, you need several things. One is so the sun is here and the Earth is here, and Venus is here and Mars is here, right? So the Earth is at a distance such that if you have liquid water at the surface, first of all, you have to have a pressure, you have to have an atmosphere. I mean, the moon is in the sun's habitable zone, but there's no water on the moon. Why is that? Because there's no atmosphere. You need pressure in order to keep liquid water on the surface. All right, and the moon has no atmosphere, therefore it has no atmospheric pressure. The Earth has atmospheric pressure, and it has an atmospheric pressure high enough to keep liquid water liquid. And so it's really a pressure requirement. And a pressure requirement, how much atmosphere does a planet have? Well, that depends on the mass of the planet. If it's small, it has no atmosphere. If it's gigantic, the whole thing is an atmosphere, like Jupiter or Saturn. But if you're in between, if you've got a rocky planet, then you have enough gravity to hold on to a substantial atmosphere. That substantial means you have enough pressure at the surface of that rocky planet to keep the thing wet. So that's that's usually a forgotten part of habitability. Not only are you at the right distance for the right temperature, but you also have to be the right size to hold on to an atmosphere to keep the pressure at that distance from the host star sufficient to have water.
Yeah, okay, right.
But also water is something that disappears. It evaporates, right? I mean, if you look up at the sky right now, there are clouds up there. Well, what happens to those clouds? If they get that's H2O. If you get that high enough, the H2O is dissociated into hydrogen and oxygen, and then the hydrogen just escapes. Because it's so high and so volatile, it's a very, very light gas, and so it has a higher velocity than the other gases like O2 and CO2 and N2. So the hydrogen escapes, and hydrogen is escaping from every single rocky planet in the universe. And so when you're losing hydrogen, you're losing the ability to have H2O. So the ability for a planet to maintain H2O at its surface depends on how rapidly that H2 is devolatilizing into outer space. Okay. So that's another thing to consider.
Right. Where's the hydrogen going once it goes out into space?
Into space.
Just out.
There's a lot of space.
There.
There's a lot of space to hold as much hydrogen as you want, believe me.
Okay. About the habitable planets, since the James Webb Telescope has been operational, there's been I'm saying thousands, there's probably been even more of those types of planets that could be sources for life.
Well, first of all, it's not been the James Webb Space Telescope that has discovered these things.
Okay.
There are about 6,000, maybe even 10,000 planets discovered or semi-confirmed, and James Webb Space Telescope has been responsible for almost none of them. What James Webb can do is look very sensitively at the atmosphere. So when you have a star and a planet transits in front of that star, then the light from that star goes through the atmosphere of the planet, and that light going through the atmosphere, then if you have a spectrogram of it, you can then tell what gases are in the atmosphere. That's what the James Webb Space Telescope can do, and that's why it's so exciting, because it can help us probe what are the gases in the atmospheres of those planets.
Okay, right. Is that like foolproof, 100% sort of correct when it's doing that, or is there sort of some margin for error?
I wouldn't use the word foolproof. What I would say is that it is very hard to do, and there's a lot of noise. And what you can usually do, you can do it more easily with large planets because they have thicker atmospheres through which more light comes, and you need light to come through the atmosphere in order for this to work. If you have a very small planet like the Earth, the layer of the atmosphere of the Earth is like the skin of an apple on an apple, and so it's a very, very tiny fraction of the light that goes through that atmosphere, and so it's much, much harder to do with small planets like Earth, but it's much easier to do with larger planets like Saturn or Jupiter. So I would say it's a wonderful technique. It's interesting. But it's very hard to do because the signal to noise ratios are so low.
When we do get more details and experiments from somewhere like Mars, are you expecting to find some at least like microbial fossils or anything around, or the evidence that there was life?
Yeah, I think it's very likely, maybe even probable, that there used to be life on Mars. It's much less likely that there's extant life on Mars. It's alive today, but it's still possible. So we know that there's water on Mars. We know that as you go deeper into Mars, it gets warmer. There's lots of water. Matter of fact, I think if you took an average piece of the Earth and a piece of Mars and you squeeze it, you could probably get more water out of squeezing Mars.
All right.
Yeah, the Earth doesn't have that much water. It's just that it's at its surface, and the inside is not so water rich.
Did you think that there could be any information that actually comes to surface that would, disprove your Gaian Bottleneck theory, apart from finding lots of, types of life that you wouldn't expect?
Well, if you could show that the idea of Gaian regulation is not something that works, or is it doesn't evolve, then that would be evidence against it. I guess if you could show that there was life everywhere, then life it's not a bottleneck. It's just Gaian regulation is something that's very common. So what we're speculating in the Gaian bottleneck is that early regulation of a planet's habitability is. We're speculating that it's rare, but it could also be, hey, maybe this is something that's easier than we thought. And in which case, you wouldn't have a bottleneck at all. But you'd have early Gaian regulation, but it would not be a bottleneck.
Yep.
But to show that was the case, you'd have to find life all over the place.
How much do you think will, again, lots of speculation here, in the next sort of 20 to 30 years with, increases in technology and everything, what's the hope that will be discovered and things that will come to the surface to sort of, maybe boost your biases and ego?
Well, boosting my ego is not high on my priority list.
Still could happen though.
And boosting biases is also not high on my priority list. Well, I'm a scientist, so we like to see evidence. So independent of where that evidence takes us, so we are ego-free enough to follow the evidence. At least that's one of the requirements of being a scientist, that you have to put your ego on a leash and follow evidence. But I do have lots of high hopes that in the next 10, maybe 100 years, there will be lots of evidence, because a lot of science is interested in this question, are we alone? And to answer it, we need to probe the Earth-like planets let's say in the nearest 100 light years or so. And the technology to do that is increasing rapidly, not rapidly enough for those of us who are in a rush, but rapidly by the standards of science so far. It's almost like a Manhattan Project to find life elsewhere. It is that important a question, maybe even more important than being able to kill your enemies. And so a lot of scientists are getting more and more interested in this question, are we alone? And matter of fact, I have a website called arewealone.us, and I can recommend that to any of your viewers who are interested in this question, are we alone? It's called Are We Alone? Well, how did we get here? The idea being that if we knew more about how we got here, we would know more about how life elsewhere would have gotten wherever they are. So I have a lot of, I think that human technology, if we keep ourselves alive, I think that there's a big chance that we're going to kill ourselves. I think the polarization in the social media and the AI is, I think that, I'm not sure AI is that interested in knowing about other AIs as much as we are interested in other life forms. Maybe it is, I don't know, but there's so much volatility in high technology that trying to predict more than 10 or 20 years into the future is, some would say it's a fool's game, but I would say it's a interesting but highly, highly speculative project.
Yes. Definitely.
So I don't know. I don't have a lot of confidence in human intelligence, because if you kill yourself, it's not intelligence, it's stupidity. So
True.
Human intelligence is something we say is great, but if human intelligence creates weapons that kill humans, then that's not human-like intelligence. That's human stupidity, and we should recognize that and come to our senses and maybe try to be nicer to each other.
Yes, yeah, I could second that. Well, that maybe the difference between intelligence and, I guess, well, depends how you describe it, but intelligence versus wisdom, and actually, implementing what you know in a way that ultimately helps everyone, and not just your own self-interest.
Well, I think people have underestimate what intelligence is. Your brain is there, just like your liver and your stomach and your small intestines and your lungs. They have evolved to keep your ancestors alive, not to do math tests. They to keep it alive. And so the ability of your brain is they're there because they were useful to the survival of our ancestors, and not to do math tests. And so we say, if you do a math test, you're really smart. That's baloney. If you stay alive, then you're smart enough for Darwin. And that's what our human brains are for, to keep us alive. And if it doesn't do that, then it's not very smart. The same thing with the liver. A good liver keeps you alive, and if it has some spectacular technique that can solve a polynomial equation, it doesn't help to keep you alive unless it does. Maybe there are tests that you have to solve polynomial equations to be able to do other stuff. But in general, I think people forget that your brain is there to keep you alive, and if it doesn't do that, then it's not very smart.
No, not doing a very good job then. What is there? Something that comes to mind, or a few things that come to mind that you've changed your mind on recently, or in the last few years, that has been a big shift for you personally?
Well, I've become more interested in entropy and the end of the universe, and I've written a couple papers on entropy and whether the universe is getting more complex, and the role of life, and how life is part of what are called far from equilibrium dissipative systems. So I'm a physicist, and we physicists don't know how to deal with history. And evolution and biological evolution are historical sciences, but physics is definitely not. We don't like to talk about history, but life is a historical science, and so trying to incorporate our understanding of life into a physical understanding is something that's, I think, very important that I've become more interested in. As to something I've changed my mind about, I think maybe about, I go back and forth about the origin of life. There seem to be two camps in the origin of life field about whether life got started on Earth at hydrothermal vents 2 or 3 kilometers down at hot springs, or not hot spring, but hot vents that are coming out of the ocean, the floor of the ocean, and there's lots of chemical disequilibrium there and lots of interesting non-equilibrium chemistry that's happening there, and there's a whole field of people who think, oh, that's where life got started. On the other hand, there's a whole group of people who think, no, you need a warm little pond at the surface. You need to have liquid, air, and rock surfaces together. At the bottom of the ocean, you only have rock and liquid. You don't have gas. And so the idea of needing gas, liquid, and solid, and potentially UV radiation to get things started, potentially the dehydration-hydration reactions that occur because the moon was 10 times closer. The day was like a third of its length, and so you had 2-kilometer tides every couple of hours coming in and out and in and out. So gigantic tides. And so lots of hydration and dehydration were occurring, but that would be only at the surface. Now, on the other hand, so those are two, and so they seem to be incompatible. But what's interesting is maybe 4 billion years ago when life got started, instead of having the surface and the bottom of the ocean, maybe it was more like this. You see, right now, the Earth is like this. There's 4-kilometer deep ocean basins, and then you have continents. Well, that dichotomy probably didn't exist 4 billion years ago. Maybe it was more like this. So maybe if you combine those two models and say, well, we've got hot springs near the surface, when the surface and the water is only, I don't know, half a meter deep or so, then you can have hot spring. You can have both models combining at the surface. So maybe that's the case. I do not know. I'm not somebody who knows that much more about the chemistry at the origin of life. I am kind of interested in some of the conceptual ideas about it.
Would you mind going into any of those?
Well, for example, I was just at a meeting in where was it, the Royal Society, and there's a guy named Ford Doolittle, who's a microbiologist, who's I guess you call him a theoretical biologist, and they're thinking about what does Darwinian evolution mean. So NASA and probably 90% of the community interested in the origin of life define life as a chemical system capable of Darwinian evolution. Well, then you have to say, well, what is Darwinian evolution? The people who have defined Darwinian evolution I call post-Cambrian zoologists. And that is, they're only interested in the life forms since about 500 million years ago. And they're only interested in species and sexual reproduction. But sex is something that's an add-on to life. For the first 2 billion years, there was no sex. And in fact, there was no death on Earth. You know, we say, oh, life means death. Well, that's only if you're sexually reproducing. If you have a bacteria, what do? They fission. They go boop, then they go boop, and then they go boom. They don't necessarily die. We, or as we're speaking, are aging. It's called senescence. That's built into organisms that have a division between their somatic cells and their germline cells. You know, here's your sperm and here's your body. Your body's going to die, and your sperm is what passes you on to the next generation. Well, in bacteria, it's not like that at all. You go boop, and then you boop, and then you divide. So the idea of sex and death evolved together, but that's very, very recent, only 2 billion years ago. So the first 2 billion years of life on Earth, there were no species, there was no sex, and there was no death. So you need to throw out all of that recent baggage in order to if you want to apply an understanding of evolution to the earliest life forms. So that's something that I've become interested in, and I want to try to figure out more and more about how Darwinian evolution or Lamarckian evolution, or how biological evolution in general could get started. I say Lamarckian because, Darwinian evolution is you don't acquire traits. You don't acquire traits are not passed on. But in bacteria, I'm a bacteria. Here it is, a bacteria. Along comes a gene goes inside and says, oh, that's something useful. It does something useful for the bacteria, and then it gets incorporated into the bacteria. And then when it goes like this, splits, it passes it on to the next generation. That's called horizontal gene transfer, and that's what we do not know how to do. But bacteria, and for the first 2 billion years, that was probably the most prevalent way of exchanging information. So that's called Lamarckian evolution, not Darwinian. So we have to shift from Darwinian to Lamarckian, and maybe if you don't have isolated organisms with cells, then it's hard to know what you're talking about, but I think we need to discuss the different stages in the... Well, for example, some people think in order to have life, you have to have cellular life. And I've done a survey of biologists, and I've asked them, the most common organisms on Earth are viruses. By far, they seem to outnumber bacteria by about 10 to 1, maybe even more. And so, are these the most abundant organisms on Earth? Are they life or not? And half of biologists will say yes, and half will say no. Now, that's after interviewing about 30, 40, 50 biologists. But then I said, I'm dissatisfied with that. I'm going to interview more. Matter of fact, I interviewed them for this course called Are We Alone.us. So then I interviewed about 200 biologists, asking them the same question, and instead of having 2 answers, yes and no, I got about 4 answers. 25% said yes, 25% said no, 25% said I don't know, and the other 25 said the question doesn't make sense. So these are biologists, specialists, who know more about life than anybody else, and they do not know whether the most common organisms on life are life. So that tells us that we don't really know what life is. I think that's the big message. We do not really know what life is. And another aspect to this unknowing is that we don't know whether an ecosystem is alive. Is the biosphere alive? This is what's important for understanding Gaia. Is the biosphere alive? And I think the answer is, well, maybe I would say sure, why not? I'm not so bothered by defining life because, as Nietzsche said, anything that evolves cannot be defined. He said this in the Genealogy of Morality, I think. I'm not sure which page. But his point was thinking like the number pi, right? 3.14, blah, 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 blah. That is not something that evolved, and it can be defined. But something like an eyeball, that did evolve. So therefore, eyeballs cannot be defined. What does that mean? Well, let's look at the history of the eyeball. I have an eyeball right now. There it is, my eyeball. And if you go back to my ancestors, my mother, and then hold her grandmother, and then my great-grandmother, etc., and you hold hands of these mothers, and you look at their eyeballs. If you go back about 300, 400 million years, you'll still see something recognizable as an eyeball. You go back another 200 million years, you say, ooh, that's not what I meant by an eyeball. You go back another 200 million years, ooh, that's not an eyeball at all. Then you go back another 200 million years, ooh, that's a proto eyeball. That's a photosensitive light spot. You go back another 200 million years and say, oh, that's something that's used to, do something else. It's like photosynthetic. It's used to harvest the energy but it's not it's not an eye. So that everything in life is like that. Everything that is evolved, if you go back far enough, it disappears. It gets deconstructed. It gets turned into a proto, and it gets earlier and earlier version of itself, which essentially is deconstructing or undermining any definition you have for the thing you started with. So that's what Nietzsche meant by if it evolved, you can't define it.
I saw in a couple of your videos that you mentioned Carl Sagan was someone that had a real influence on you, and I think you described him as a big mentor.
Yes.
So he wrote, "Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves." What does that mean to you now, and do you think he was correct?
Well, interestingly, so yes, he was a gigantic influence on me. Particularly when I was in college, I read the book The Cosmic Connection, and I can recommend that to anybody who wonders who they are and how they got here, because what he does is tells us about how the Earth and biological evolution happened and how did we get here. That's if you're interested in your. I had a gigantic identity crisis. Let's just say this. I said, who in the hell am I here? What am I doing? Why should I care about anything? And he pointed out, the deep connection that we all have in how we got here. And so I've been a big admirer for Carl Sagan for a long time. On the other hand, when I started to do work on the evolution of human-like intelligence, I would say, no, Carl's completely wrong on this issue. In 1995, he had a long series of debates with a guy named Ernst Mayr, and Ernst Mayr pointed out that human-like intelligence is not a convergent feature of evolution. We should not expect it elsewhere. But Sagan's view on this was just the opposite. He thought, oh yes, there are many different ways to intelligence, and so there's so many ways that we should expect it elsewhere. So I disagree completely with Carl on that point. However, the quote you mentioned, I agree with him completely, that we are in danger of killing ourselves and we should not rely on help from there's no sign that there's any help from elsewhere that's going to come intervene and act as a mediator between us and ourselves to keep us from committing technological suicide. I think that's a very high possibility, and so did he. He was concerned about that. That's why he studied nuclear winter for the last 10 years of his life, I think. So I agree with the potential that he saw of us killing ourselves. He was very worried about it. He did something about it. I'm not sure I can do anything about it other than to suggest that it's something that's very important that might happen to us. And the Fermi paradox might be one piece of evidence that suggests that this happens to other technological civilizations.
So what are you been working on most recently then?
Most recently, I've been working on this idea of a third law of thermodynamics in which not just entropy increases, but the rate of production of entropy increases. And so if you look at life forms or hurricanes or convection cells, these all belong to a group called far from equilibrium dissipative systems. They dissipate free energy. And free energy is like, excuse me, free energy is like coal or uranium or sunshine or anything that can do work is free energy. Now, people get confused about, conserving energy because people are saying, you need to conserve energy. Well, the first law of thermodynamics is that energy is conserved. So to tell people to conserve energy is assuming that the first law is violated. No one can violate the first law of thermodynamics, and that is energy is conserved. So it doesn't make any sense at all to say conserve energy. On the other hand, to make sense out of those statements, what you need to do is distinguish between energy and free energy. So you can imagine that if this whole room everywhere around you was really, really, really hot, but it was the same temperature everywhere, like the universe used to be, it's very, 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 very hot everywhere. Well, there's lots of energy, but there's no free energy. Free energy means it's hot over here, cool over here, and then you can use this heat to expand a piston and push the car up a hill. Internal combustion engines work that way. You take oxygen, you take the petrol, and then it burns, it expands, and then it pushes, does work. But you can imagine if the whole Earth were filled with benzene, you couldn't do anything. Or if it were all filled with oxygen, you couldn't do anything. Well, I was teaching planetary science, and we found out that on Titan, there's methane and ethane. These are things that are very, be great to have them on Earth. You could burn them. But they said, oh, that's very dangerous on methane. You don't want to light a match on Titan, rather. And I said, that's crazy. There's no oxygen on Titan, therefore it's not dangerous at all. You have benzene and there's no oxygen around. There's nothing flammable because you need the oxygen to inflame it. So that there's a difference between energy and free energy. Energy can be really, really, really hot things, but if there are no gradients, if there's no difference between hot and cold, then you cannot do any work. But if there are chemicals over here and chemicals over here, and you can combine them to produce a reaction, then you have free energy. So that's the difference between. So what they're talking about when you conserve energy, they're talking about conserving free energy. That's just a sidebar for those who haven't studied physics, I guess.
Yeah.
So what I'm concerned with is whether life forms and hurricanes and convection cells, whether they form in ways that dissipate free energy as fast as they can. Is there a tendency for life to evolve in directions, not to increase the complexity of life, but to access and dissipate free energy as fast as it can? And that's a model, it's a theory, it's something that I think describes the evolution of life, because most people think the evolution of life is, it's getting more complicated. And, they can't define what complexity means. But I think a way to quantify the direction of evolution is by asking, is the direction of life towards an increase in the rate of entropy production? So that's an idea that I've been interested in lately.
Yeah, cool. Well, we might wrap up there, I reckon, Charlie. So you mentioned one of your websites where people can find out a little bit more and do that sort of online course. But is there any other resources that you think are worthwhile mentioning?
Well, for those of you who want to dig deeper, for example, you can just Google my name and look at my publication list. And we talked about the Gaian Bottleneck. That was a paper we published in 2016 in the journal Astrobiology. And the author was my PhD student, Aditya Chopra, and myself. So you can just Google my name and look at like Google Scholar is a good way to do this. Just Google Scholar and then put my name in there, and you can see a list of publications that what I've written about. I've also written about cancer with Paul Davies, for example. We've written about other things with Paul Davies, but we've written about half a dozen papers about a new atavistic model of cancer. And the reason we've done that is because doctors, as astrobiologists, we've studied the 4 billion year history of life on Earth, and we think that that has something to do with cancer. Doctors don't study evolution, and so they would be ill-placed to understand this. And so that's why there is room for an astrobiologist to contribute to the fundamental understanding of cancer.
Okay, I briefly skimmed over a little bit of that, of what you're working on recently, but it went over my head, so I'll have to do a bit more reading so I can learn a bit more about that, because it sounds very promising and very interesting. But yeah, thanks so much for your time today, Charlie. I really appreciate it. You've got a great way of explaining things, and I'm sure people will get a lot out of hearing you do your thing. So thanks again.
Well, I hope I've made you very uncomfortable in so many different ways.
No, definitely. It's a twofold way of being uncomfortable. So I think you've ticked off a few of those boxes. So
well, actually, I think you're onto something here, because in order to explain why I wanted to travel in this identity crisis, I always tell them, I don't want to hear what I want to hear. I want to find out things that I don't want to hear. And that, I think, is a key, something very important about curiosity, that element of I want to hear what I don't want to hear. And that kind of goes against what the main theme of the sickness of being told what you want to hear and just self-flattery. So anyway, so I appreciate your efforts to overcome the barriers of self-flattery.
Perfect. I appreciate that, mate. Thanks for your time again.
All right. Bye-bye.